we are. All right. Let's see. Does everyone have some kind of an answer?
No.
Gina, what do you got? Yeah. 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 Oh, okay. Does everyone have something down for this derivative? Give you a minute. That's yeah. We could let the birthday girl answer. What do you got? Mm-hmm. Okay. Equals 0. Okay. So she set it up exactly right. Oops. Let me just say that. Oops. Nope, that's not what I wanted. All right, I'll just write it up here then. Okay, so she said secant of xy, tan of xy, and then when she went to take the derivative inside, product rule. First times derivative of the second plus second times derivative of the first. You forgot the product rule?
Angry.
I agree too. It's so tricky. We had the whole imposter conversation and everything, and all right, whenever y is inside of another function, you're going to have to distribute before you're going to be able to get all the dy dx terms. Although in this case, there was something else you can do, but because I'm trying to teach good form. Okay, technically in this one, I will say you could just divide both sides by all this over here. The secant xy, tan xy. Right, that would be like the easier way to divide both sides by. Yeah, well, it's nice. It's really quick. But just be aware that if it wasn't 0 over there, and you would have to distribute. So I think maybe I should just show you distributing. I don't know. Unless we just wait for a homework problem. We don't have to. Yeah. It is 0. Oh, that's what you did, Cameron?
Yeah.
Nice. So do you want to do a way we just divide each side by all this and we get 0? Okay. All right. So we divide both sides. We'd have x dy dx plus y. 0 over secant xy tan xy is going to be 0 still. So yeah, this one kind of worked out nicely. And then we want only dy dx terms on the left. So what do? Subtract y. And then we divide by x. So our derivative is negative y over x. Anyone get that? Ooh. Both? All right, you got it? You got it in the birthday. Nice. All right. The answers to the homework are in the back of the book, but sometimes you look up the answers and they don't look like what you got. So if you just didn't get the answer at all, or you got something and you're not sure if it's the same, go ahead and ask homework questions. And if you didn't check, you can grab a green book from the back and check the answers. You didn't have. Is there any you were confused about? 2. Wait, wasn't it odds? Oh, they're 2. Okay. Okay, what are they? 1 and 13. The 1, actually have 1. Oh, wait, no, I don't have 1 here. It's a different one. Is that 1? Yeah. Okay, let's talk about number 1 first. I have it labeled 9 because that's what it is in the other book. If you didn't get 1 right, it's probably because you forgot to use product rule. Sometimes people stop hating the product rule. All right, just deal with it. You have a product, so you use the product rule twice. So first, x squared derivative of the second, dy dx, plus second y derivative of the first is 2x. You got the second product rule right? Did you remember the derivative of 6 was 0? Okay. So you want to keep the dy dx terms on the left and subtract the non-dy dx terms. So, this is the same as 2xy. Y times 2x is the same as 2xy. So that's why I subtracted that and subtracted the y squared. Oh yeah, the y has to be there. From and you're talking about this y here I have underlined? Yeah, because you have first x, derivative of the second, 2y to the first, so 2y times dy dx. Yeah, it's a chain rule. Very good. Sneaky. It's all sneaky. And then once you subtract those terms over there, then dy dx is a common factor, so you can pull it out and solve for it by dividing. So that one was all right. What was the other one you said? 13. X squared. Oh, 13 is very similar, isn't it?
Yeah.
It's x squared y minus x squared equals 4. Oh. Oh, yeah, this one. Wait, 13 says find where the slope of the curve is. Oh, is defined. I was just getting the derivative. Okay. So did you actually get the derivative? You got that? Oh, so where it's defined is where the denominator is not 0. Okay. So let's figure out what values would make the denominator 0. Oh. So if we set the denominator equal to 0, boy, can't really do too much of this. So it'll be undefined when, let me just see what the original looks like. X squared y x squared. Even if we factor out, we could solve for y. Okay. All right, let's try doing that. Let's see. If I just move this term over to the other side, we add 2xy to both sides. X squared equals 2xy. 2x. And the other thing is, so if y was equal to x squared over 2x, it would be 0. The only thing is I don't want to just assume x is not 0. But x over 2. In the back of the book, when you look this one up, did they give specific points, or do they just want, like, in general, when y equals a half of x, or, do you remember? Did we look this one up? 4.2. Let me just see what they're looking for here. 4.2. Sorry. Quick quiz. I should close that. Yeah, well, I don't think it's going to work, right? Just have to do it. Okay, so we're looking to see when the derivative wouldn't be defined. And so that's when the denominator of the derivative is 0. And if we look at if we set the denominator equal to 0, we see it's going to be undefined if either x is 0 or if y equals x over 2. If y equals x over 2, then the denominator is going to be 0. So y equals x over 2, or if x equals 0, either way, do you see either way the denominator would be 0? That's what they're looking for there. Kind of question. You got the derivative right. Awesome. Other questions on homework? Yes. 17. Ooh, I heard an ooh. I like this one, actually. So you took the derivative of x. You knew it was 1, right? The derivative of tan y is secant squared y times dy dx. Did you get that part? Derivative? Oh, it's not? A different one? Oops, sorry. Okay, this one is x squared plus xy minus y squared. Uh-oh. Yeah, I have different numbering. And, all right, so we're just going to add it. We're just going to add it because I don't think that one is here. Can you, oh, wait, this is actually working. Here we go. All right, so 17. X squared plus xy. X squared plus xy minus y squared equals 1. They want us to find the lines that are tangent and normal to the graph at the given point. 2, 3. So all we need is the slope, which is the derivative, right? Because we got both coordinates of the point, right? When you want to write the equation of the tangent line, it's it's going to be y minus 3 equals, now we're going to have to get the derivative at that point for the slope, but then the rest is just going to be x minus 2. So the slope for this one is just going to be whatever the derivative is when we evaluate it at that point 2, 3.
I didn't know how to get the y. The second foot of the y.
Oh, then they gave it to you. But if they didn't, though, if they didn't give that to you, you just put it into the original function, a 2 for all the x's. You'll have a quadratic, but then you can still solve for y. Like you can have two different answers, I guess. That was probably the problem, too. Well, do you want to get the derivative of this one, or did you get the derivative? Oh. Does everyone know if that was right? Do you want to? No? Oh, like when you plug the numbers in, you got negative 3 over 2? Okay, that's probably, all right, it takes 2 seconds. Oh, we'll just do it, and then we'll get on to today's. Okay, so let's take the derivative of both sides. So we have 2x plus, hey, Tim, guess what you got to use here? Did you say stop or product rule? You said stop. I said, what do you have to use here? You said stop. Okay, so what is it? Product rule. Okay, so what's it going to be? What is the derivative of xy? There you go, because it's times 1. All right. What about the derivative of the minus y squared? No. That's like a little math joke. No, this is first. This is your first. This is your second. So we have first times derivative of the second plus second y times derivative of the first. I didn't write it, but it's 1. Yes. Wait, when I take the derivative of y, why isn't it y dy dx? Oh, okay. So if you're just taking the derivative of y to the first, it's 1y to the 0, right? Power rule, times dy dx. What is anything to the 0? 1. Yeah. I think that's what you're asking. Which we made it look worse than it had to be. All right, so let's finish this up. Minus dy dx equals 0. Okay, so you keep the dy dx's, you move the other ones over. So we have x dy dx minus 2y dy dx equals, when we move them over, negative 2x minus y. We pull out the dy dx. We have x minus 2y equals negative 2x minus y. And then what? Y. Okay, so this is the derivative, but we have to figure out what it is at 2, 3. So we want to evaluate our derivative. So dy dx evaluated at the point 2, 3 is going to be negative 2 times 2 minus 3 over 2 minus 2 times 3. So negative 4 minus 3 is negative 7. And 2 minus 6 is negative 4. So it's 7/4. So the equation of our tangent line, we were just missing the slope. So that's where all the work came in. So the equation of our tangent line is y minus 3 equals 7/4 times x minus 2. And then for the normal line, y minus 3 equals negative 4/7 times x minus 2. Okay? I just want to make sure you guys are clear on what I mean. Yesterday we were talking about functions that are defined explicitly versus implicitly. explicitly you needed to get, just have y all by itself, or one of the variables all by itself in terms of the other. Could anyone just give me an example of an explicitly? Y equals 2x to the fourth. Is that a function that's defined explicitly? Yes. And those are nice because when you get the derivative of both sides, the derivative of the left side is dy dx. You get the derivative immediately. But implicitly defined functions require a little more work to get the derivative. Someone else, give me an example of an implicitly defined function. It can be as crazy as you want. Wait, that's your idea of crazy? X plus y equals 74,000? Because that would be just subtract the x and it would be... Wait, 9? Like xy to the 11th like this, or was the whole thing to the 11th? Oh boy. Oh boy. That's what I'm thinking. Okay, so plus 10x. Let's put some y's on the other side too. Let's go crazy. Let's make it a mess.
9,000.
What is with this 9,000? Now I just... So, all right, whatever it is, but as long as you don't have one variable all by itself implicitly. Now you will. I'm going to copy and paste this right into a test. Okay. So yesterday we talked about how to find the first derivative of an implicitly defined function, and today I want to talk about getting the second derivative. That's easy. So the first step to get the second derivative is get the first derivative. So everything we learned about yesterday. Then, if you have the first derivative, what do you got to do to it to get the second derivative? Take the derivative of that. So you get the derivative. Then you take the derivative of that of both sides, because the derivative of the first derivative is the second derivative. And remember this notation? Right? When you take the derivative of the first derivative, remember that notation? We call it, for the second derivative, we use d squared y over dx squared. Remember where that comes from? You just see it. It looks like d, dy, looks like d squared y. So that's just, you have to remember how to write it. Okay. Then once you get the derivative of the derivative, you might have a few dy dx's in it. You just got to replace them. Just put in there whatever dy dx equals. You'll know it because you will have already found the first derivative. And then if they say at a particular point, you got to plug in the coordinates. That's fun. So our first example, we've got x squared plus y squared equals 25. What does the graph of that look like? Circle. Where's its center? The origin. And the radius is 5. So basically, we're asked to find the second derivative of this graph at the point 3, 4. Do you think that the second derivative at the point 3, 4 is going to be positive or negative, and why? What do you think, Ellie? Negative. Yeah, because it's concave down there. It is. Right? What about the first derivative? Do you think it's positive or negative at that point, and why? Why? Yep, because it's got a negative slope. It's decreasing. So both the first and the second derivative should be negative values at that point. Well, we'll see. So let's get the first derivative of x squared plus y squared equals 25. No products. This is awesome. Right? I know. What's the problem with the product? So what do we got for the derivative? Yes. 0. Okay. We don't have any distributing to do, which is great. Subtract the 2x. And we don't even have to factor out dy dx. It's just one term. What's left to do? So divide, right? Good, even the 2's cancel. So we have the first derivative, dy dx equals negative x over y. And by the way, at this point, 3, 4, what would the derivative be? Negative 3/4. So we don't have to write the equation as tangent, but we could, right? We know, and it is negative, so that makes sense. But we're moving on. We're getting the second derivative. So we're going to take the derivative of both sides. If we take the derivative of the left side, what do we get? Good. That's how we write it. It's the second derivative, but d squared y over dx squared. Just remember what the little squares get. Ooh, who wants to take the derivative of the right side? It is a quotient. Yeah, this is a quotient this time, Miss Apple. Oh, they were just the products. Is this good? It's really not that sneaky. Because, it's like, maybe if we, I don't have my highlighter. I would highlight all the operations. All right, here we go. Low D high, what should I write for that? Y times negative 1. So can we write negative y? Sure. Why not?
All together at one time.
Oh, y times negative 1. No, don't do that. Less high, D low. So think about what we're going to write. Thank you, Tim. Plus x dy dx. Right, because it's minus negative x times dy dx. Minus negative. All over. Beautiful. Okay, so we got the second derivative. We took through both sides, but we don't want our second derivative in terms of the first derivative. We want it in terms of x and y. So we're going to replace any dy dx with its equivalent. What does dy dx equal? Negative x over y. So wherever we see a dy dx, we're going to substitute in negative x over y. So our second derivative is negative y plus x times negative x over y all over y squared. Now, they're not asking us for the general rule. They just want to know what it is at a particular point. But if I did have to clean this up, how would I get rid of this fraction in the numerator? What could I multiply numerator and denominator by so I wouldn't have a complex fraction? Oh, no, you do. Yeah, but it's still over y. I still have a fraction in the numerator. I don't like fractions of, in a numerator or a denominator. Any ideas what we could multiply? Yes. Oh, whoa. I'm thinking easier. What could you multiply each term by so that you wouldn't have a fraction? Y, right? If you multiply the numerator by y, and then of course the denominator, so you're really only multiplying by 1, if you distribute that, you're not going to have any more fractions in there. So if you distribute the y in the numerator, what's the first term? Negative y squared. Think about what the second term is going to be. No, not ugly. If that y would knock out the y in the denominator, so what would you be left with? Right, you cancel this one, so you're left with x times negative x, otherwise known as negative x squared. And what about in the denominator? Y squared times y. So here's the second derivative, looking very nice. And then because they asked, if they just asked the second derivative, we'd be finished. But this here, we have a step 4. They want us to tell them what the second derivative is at that point. I believe it was 3, 4. So we're just going to plug in a 4 for the y and a 3 for the x. And if we do that, negative 4 squared, negative 16 minus, hopefully it'll be a negative number, right? Because it was concave down. 4 cubed. Nice. Nobody said 12, which is awesome. Oops. Oh, the kids. The exponents, multiplication, all confused. So we get negative 25 over 64. Woo. That's not ugly. And it's negative, which makes sense because our graph was concave down at that point.
So,
Why did you go ahead to the next one?
no,
Well, you know. So yeah. Yeah, I just try to see if we can try one more of these. I never know where to. We want to get the second derivative of this one at the 0.31. Now, I don't have any predictions for this one, although it looks like it's going to be a hyperbola. We'll see. We'll see what it's going to be. What's the first step? Yes, so we got to take the derivative of both sides. So derivative of the x squared, that's no problem. You know, it's a sum and difference of terms. You do each one separately. So we got 2x. Okay, what are we going to use to find the derivative of 2xy? Product rule. Now, what I like to do, so I don't have to, you know, you could just do the product rule in xy, but then you would have to distribute the 2 afterwards. If you like to save steps, just make your first the 2x and the second the y. When you use the product rule, then you won't have to distribute the 2 afterwards. If you just include whatever the coefficient is in, you won't have to distribute. But it's okay if you don't. All right, so first 2x, derivative of the second. Y dx plus the second, y times the derivative of the first. What can I write for that? Second times derivative of the first. Yeah, 2y. It's y times 2. I just wanted to see if you guys were okay with 2y. All right. Minus 2y dy dx equals 0. All right. So let's keep the dy dx terms, this one and this one, and we'll move by subtracting the non-dy dx terms. So we have 2x dy dx minus 2y dy dx equals negative 2x minus 2y. And then we can divide out the dy dx and divide. Sometimes I like to do it all in one step, but I won't. Oh, yeah, now I'm dividing. Now that's our first derivative. We can divide through by either 2 or negative 2 to clean it up first. What would you rather divide through by? 2 or negative 2? It's up to you. 2? You have a lot of negatives left. You okay with that? Negative 2. So then it'll be our first derivative. We divide that by negative 2, we get x. And we have plus y, right? This will be negative. And that'll be plus y. I don't know if we can do it. Okay, now we want to get the second derivative. So derivative of the first derivative is the second derivative. What do we get to use this time? Quotient rule. So it's low, negative x plus y. D high. Yeah, this one is kind of ugly. Derivative of x plus y would be 1 plus dy dx. So low d high, less high, low, which should be negative 1 plus dy dx, all over the denominator squared. Now, if they wanted us, we have to put in for dy dx, you know, the one thing we have to replace all the dy dx's with x plus y over negative x. Somebody thinks it's beautiful. So yeah, everywhere I see it, I have to write in x plus y over, well, I should have written that as y minus x, but it's negative x plus y minus x plus y times negative 1 plus, oh, what was that again? X plus y over negative x plus y. I know, it's kind of crazy. Now, I'm not going to worry about trying to clean that up, but we do have to plug in the coordinates of the point. So the point was 3, 1. So we want to get the second derivative at the point 3, 1. Negative 3 plus 1 would be negative 2. 1 plus, oh yeah, we should figure out the derivative there. If 3 plus 1 is 4 over negative 3 plus over negative, that would be negative 2. Oops, that's a minus. No, it's not terrible. Minus x plus y, that's 4, right? 3 plus 1 is 4. Oops. Times negative 1 plus, I already figured out that derivative of negative 2. All over negative 3, so plus 1, that's going to be over 4. This comes out to be, what is it, 7/4? That comes out to be 2 plus 12 over 4. Oh yeah, no, 14/4, which is 7/2. Woo! So you get to try some on the handout. Excited? It's not like conceptually much harder than what we did yesterday. I mean, you take the derivative of the derivative. It's just you got to plug in the first derivative, and then sometimes.
I did it the really long way.
What?
I did it the really long way. Plugged in x, y instead of.
Oh,
I love this class.
I'm recording. And Jared Gibbs just said he hates this class, and I'm recording. I don't know. I hope they didn't hear Jared Gibbs say he hates this class.
Oh no, I love this class.
You're a liar.
This is my favorite class.
Oh, yeah, well, I'm still recording. Oh, well, they have the steps. You can go back and look at your notes. Fill in the steps, kids. Wait, did I stop it? Where's the recording? There we go here. Okay, stop.